Good morning to everyone. I am Sweta from JMRP Gachwell. In this video lesson, I am going to discuss about state the need for microwave devices, distinguish between ordinary semiconductor devices and microwave semiconductor devices, define gun effect, list the applications of gun diode, explain the working of impact diode, list the applications of trapper diode, state the need for microwave integrated circuits, that is MICs. Next, list the applications of microstrip antenna. Okay, so first of all, we will discuss about state the need for microwave semiconductor devices. So, in this, so here the microwave semiconductor devices used for the modulation detection, microwave signal generation, microwave amplification and control of electromagnetic radiation with wavelengths from 30 centimeters to 1 millimeters, that is the frequencies from 1 to 300 gigahertz. So for this purpose, we are using a microwave semiconductor devices. So here in the available devices for generation and amplification of microwaves are conventional semiconductor devices and microwave fuse, but these devices have the following shortcomings. So the limitations of conventional transistor at microwave frequency and the limitations of microwave tube is generation of microwaves required higher anode voltages and high magnetic fields for focusing the beam. Special types of waveguides are required for guiding the waves. So the devices are bulky, cost is more and required high voltage sources, hence the microwave semiconductors are used for low cost applications. Okay, so the variety of microwave semiconductor devices are used for the various applications like wireless communications, optoelectronics, spacecraft communication, radar communication and overall voice data also, TVs and telephone communications are transmitted long distance by microwaves between ground stations and communication satellites. So because of these applications or large number of applications are there in microwave semiconductor devices. Okay, so these microwave semiconductor devices mainly used in wireless communication, optoelectronics, spacecraft communication, radar communication and the TVs and telephone communications also we use these radars. And advantages of these microwave semiconductor devices are smaller in size, light in weight, low cost, low power consumption, low noise, high reliability, low losses, high power handling capability. Because of these advantages, microwave semiconductor devices are used. Okay, the size of microwave semiconductor devices is small, light in weight, low cost and low power consumption, low noise and high reliability, low losses and high power handling capacity. So because of all these features and advantages, we are using a microwave semiconductor devices. Okay. So next one is distinguish between ordinary semiconductor devices and microwave semiconductor devices. Okay. So this is an ordinary semiconductor device. Here we are considering here microwave semiconductor device. Consider a parameter that is the frequency range. So the frequency range used for below UHF range, we use normal semiconductor or ordinary semiconductor devices. Coming to the frequencies above 1 GHz, we use microwave semiconductor devices. That means microwave frequency range, we use microwave semiconductor devices. Next, power handling capability here is low. Coming to the microwave semiconductor devices, power handling capability is high. Next, operating temperature is low. Here the operating temperature is also high. Cost is here low, here high. Coming to the materials used, here we are using a silicon and germanium for a normal semiconductor devices or ordinary semiconductor devices. Coming to the microwave semiconductor devices, we use silicon, germanium, gallium arsenic, indium phosphide, cadmium telluride and indium arsenide. So these materials will be used here for microwave devices, in microwave semiconductor devices. Coming to the ordinary semiconductor devices, we use only silicon and germanium materials. So this is distinguish between normal ordinary semiconductor devices and microwave semiconductor devices. Okay, next topic is define gun effect. Okay, so here before gun effect definition, so actually microwave semiconductor devices are divided into two types. One is avalanche transit time devices, one more is transferred electronic devices. Okay, so in avalanche transit time devices, we have impact diode, barrett diode and trapper diodes are there. And coming to the transferred electron devices, we have gun diode, tunnel diodes are there. Okay, so coming to the gun effect. So here the gun effect was discovered by J.B. Gunn. Okay, gun effect was discovered by J.B. Gunn in the early years of 1963. That is in the early years of 1963, the gun effect was discovered by J.B. Gunn. Okay, so the materials such as gallium arsenide or cadmium sulfide exhibit an interesting effect of conductivity known as gun effect. Okay, so in the year of 1963, J.B. Gunn discovered the transferred electron effect, which is now commonly referred to as a gun effect. This is nothing but a electron is transferred. So transferred electron effect is called as a gun effect. Okay. So this effect is utilized in a gun diode for generation of microwave oscillations in a bulk semiconductor materials. Okay. So in the year of 1963, J.B. Gunn discovered what he discovered? Transport the electron effect. Okay. So transformation of electron is called as a Gunn effect, that is utilized in the gun diode for generation of microwave oscillations in a bulk semiconductor material. Okay. So when a DC voltage is applied across the gallium arsenide, an electric field is established across the slice of the gallium arsenide, that is in the middle layer. So this electric field across the gallium arsenic is 3.3 kilovolts per centimeter. Okay. So one see here. Okay. So whenever we apply a DC voltage that is across the gallium arsenide, so at that time an electric field is established across the slices of gallium arsenide, that is in the middle layer. Okay. So this electric field across the gallium arsenic is 3.3 kilovolts per centimeter. Okay. So even though there is no PN junction but called a diode with respect to the positive and negative terminals of the DC bias applied. Okay. So here we are applying a DC bias with respect to positive and negative terminals. So here as the DC bias, that means applied voltage is increased, the current through it also increases. That means it has a positive resistance up to the applied voltage less than the 3.3 kilometers. So up to so one see here. So when the applied voltage must, so here we are using no PN junction, but here we call as a diode with respect to the positive and negative terminals of the DC bias applied. So here as the DC bias is increased, so if we are increasing the DC bias, that is applied voltage is increased, the current through it also increases. Okay, the current through it also here increases. As the voltage is increased, the current is also increases. That means it has a positive resistance. That is, if the applied voltage increases, the resultant current is also increases up to the applied voltage less than the 3.3 kilovolts per centimeter. So up to 3.3 voltages, whenever the voltage is increases, the current is also increases. So after that, when the applied voltage must be exceeds the threshold voltage value, that is up to 3.3 kilovolts per centimeter, the current, here once you see the diagram, the current decreases with increasing in the applied voltage, result in a negative resistance effect. Okay. So after the threshold voltage, even though the voltage is increases, the current will be decreases. Okay. If the applied voltage increases, the current through the device is decreases is called as a negative resistance. So that's why we call it as a negative differential resistivity region. Okay. So this negative resistance property is used to produce the oscillations in the microwave frequencies. Because of this property, these used to produce the oscillations in the microwave frequencies. So here the gun effect is exhibited by semiconductor materials like gallium arsenide, indium phosphide, cadmium telluride and indium arsenide. So here the gun effect is exhibited by the semiconductor materials like gallium arsenide, indium phosphide, cadmium telluride and indium arsenide. Okay. So this is about gun effect. Definition of gun effect. Next, the applications of gun diode. Okay. So coming to the applications of gun diode, we use this in radar transmitters, that is police radars or CW, Doppler radars. We use this gun diode, and pulsed gun diode oscillators used in transponders for aircraft, that means air traffic control, and in industry telemetry systems also we use, and broadband linear amplifiers, fast combinational and sequential logic circuits, low and medium power oscillators in microwave receivers, and pump sources in power amplifiers also we use. Okay. Next, working of impact diode. So here impact, the word impact is an acronym for impact, ionization, avalanche, transit time. Okay. The word impact diode means impact, ionization, avalanche, transit time diode. Okay. So it is an RF semiconductor device that is used for generating the microwave radio frequency signals. Okay. So it is an RF semiconductor device that is used for generating the microwave radio frequency signals. That is microwave radio frequency signals is that is about 1 to 300 gigahertz signals. Okay. So the main advantage of this microwave diode is its relatively high power capability, and coming to the disadvantage is more noise. Okay. Advantage is high power capability, and coming to the disadvantage, noise is more. Okay. So here the impact is a diode, the junction being between the P plus and the N layers. Okay. So once see here, so here impact, it is a diode, the junction being between the P plus and N layers, P plus and N layers, that is two regions can be considered regarding the operation of the impact diode. Firstly, the drift region. Okay. And secondly, the avalanche region. Okay. These two regions provide different functions. The avalanche region creates the carriers which may be either holes or electrons, and the drift region in which the carriers moves across the diode taking a certain amount of time dependent upon its thickness. Okay. So the impact diode and its characteristics, the characteristics of impact diode is shown here. So one see here. So here the impact diode is operated under the reverse bias condition. These are set so that breakdown occurs. This occur in the region very close to the P place, that is heavily doped P region. Heavily doped P region. A very high voltage, that is 400 kilovolts per centimeter is applied to the impact diode, resulting in a very high current. Okay, so one see here 400 kilovolts per centimeter. A normal diode would easily break down under such conditions, but impact diode is constructed that it can withstand these conditions repeatedly. Due to high potential gradient cause a flow of minority carriers crosses the junction, it is now assumed that oscillations exist, and we may consider the effect of positive swing of RF AC voltage superimposed on the top of the high DC voltage. Okay, so see here, applied DC voltage. The increases velocity of the electrons and holes results in additional electrons and holes by knocking them out of a crystal structure by so-called as impact ionization. The process continues of creating additional carriers at the junction, and it now snowballs into the avalanche. If the initial field was at threshold of allowing this avalanche is not instantaneous, the whole process takes a time such that current maximum at the junction occurs at the instant when RF voltage across the diode is 0 and going negative. So here a phase shift of 90 degrees between the current and voltage have been obtained. So here the current pulse at the impact diode is situated at the junction. So however it does not stay there because of the reverse bias. The current pulse flows to the cathode at a drift velocity depending on the presence of the high DC field. Okay, so here we have a high DC applying. So here the time taken by the current pulse to reach the cathode is proportional to the thickness and velocity of the high doped N plus layer. The time taken for current pulse to move from the position of V is equals to 0, the position of V negative, maximum of RF cycles is 90 degrees phase shift. So this impact diode is useful for both oscillators and amplifiers also. This will be used for both oscillators and amplifiers also. The resonant frequency of impact diode is F0 is equals to U D by 2L. The efficiency of impact diode is beta is equals to PAC by PDC, that is equals to VAC by VDC into IAC by IDC. Here neta is an efficiency and PDC is AC and DC voltages, VDC and AC and DC powers. This is AC and DC voltages, this is AC and DC current. Okay, so coming to the disadvantage of this diode is it is very noisy because avalanche is a noisy process, and tuning rate is not as good as in the gun diodes and amplifiers. And coming to the applications, microwave oscillators, local oscillator in receiver, useful in FM, telecommunication transmitters, low power microwave oscillators, CW Doppler radar transmitters, police radars, parametric amplifier pumps. Okay, so all these applications we use these impact diodes. Next, applications of trapper diode. So trapper is trapped plasma avalanche triggered transit diode. Okay, trapped plasma avalanche triggered transit diode, which is also belongs to the same basic family as the impact diode. The trapper diode is high efficiency microwave generator. Trapper diode provides a much higher efficiency than the impact diode. These are used in low power Doppler radars and local oscillators in radars, used in microwave beacon landing systems, used in radio altimeters, used in phased array radars, used as a local oscillator for radar, microwave beacon landing systems, radio altimeters and phased array radars. Next, need for microwave integrated circuits. So here a microwave integrated circuit is an integrated circuit designed for operation at microwave frequencies, that is 1 gigahertz and more. So such components are physically small and some cases having a less than the square millimeter of square area, surface area. So here the microwave devices has a small in size, lightweight, high reliability, low power consumptions are the main advantages of microwave integrated circuits, but MICs are low power handling capability. These are both passive and active devices are grown on semiconductor substrates. Even these MICs are used in linear and digital applications also. So here the MICs are made either in a monolithic or hybrid form. Monolithic technology has some disadvantages, namely complex and difficult processing and poor performance and low yields, and hence it is not preferred for MICs. Coming to the hybrid technology is preferred in MICs. So in this technology, the active devices are mounted and the passive devices are deposited on the substrates. So it has a high quality ceramic, glass and ferrites are used as a substrate. So because of these features, we use this hybrid technology. And coming to the applications of microwave integrated circuits is cellular telephones, receivers and transmitters for wireless systems, transponders and receives for GPS, that is a global positioning system applications, and robot control systems. Okay. And coming to the applications of microstrip antenna, these are used in mobile communication. Omnidirectional patch antenna is used in mobile phones, satellite communication system, wireless communication, direct broadcast televisions, wireless LANs, global positioning systems, missiles and telemetries. Microstrip antennas are used in the fields of RFIDs and aircrafts. Okay, we use all these. once again, once. See, advantages of microwave semiconductor devices. These are the applications of gun diode. These are the applications of Untitled diode. And the applications of here trapper diode. need for MICs, microwave integrated circuits, and applications of MICs. And applications of microstrip antenna. Thank you.